now you have an idea about how these multivariate Gaussians look like and what this covariance matrix means, or how it kicks in the correlation or covariance between individual directions in space. All right. So now we apply this to an example, and the example that we want to look at is classification of handwritten characters A and B. So we want to predict if a given image is an A or it's a B. So what we are using for this is, so if you look at this handwritten A and this handwritten B, what you can measure is how the width of the letter, and you also can measure, give the height of the letter, right? And you can define a variable x, which gives you the ratio between height and width. And that's your random variable. So we are interpreting the ratio of width and height as a random variable. So what we assume next is that we have a lot of handwritten characters, right? And we know for each of these handwritings whether this should be an A or a B. So we have labeled data. So doing a bit thinking about the problem, we would expect that for A's, width and height are roughly the same. So we would expect our random variable on average to be close to 1 for A's, because we would assume that it's equal width and height. And the for the B's, we would accept that the average of height and width will be roughly close to 2, because it's 2 times higher than its wide. All right. So in other words, what we expect is that the distribution of the class A has a mean value of roughly 1, and the distribution of the random variable x for B's has a mean of roughly 2. What exact numbers this are? This is what we can estimate from our training data or from our set of handwritten characters. Okay, let's draw this. So we assume, because the mean value is nothing that's directly connected to the normal distribution, it's just a parameter of it, and this first order moment you can calculate for data distributions independent whether they are distributed normal or not. But we are assuming that this ratio between height width ratio will be roughly normally distributed if you look at handwritten characters that have been written from different people, right? So we would expect that this width height ratio scatters around the mean of each class. So if we draw this, if we say we already estimated that we will have a mean value of 1 for the A's, and there is a scattering around this mean value for sure, because we have different styles of handwriting. In parallel, we do see the distribution of the random variable x for our letters B. Right, so we have an average of roughly 2, and the ratio scatters around this mean value. Having extreme values, we will find only rarely in our data sets. All right. Okay, so that's the situation. So, and when you look closely here in between, this gives you the probability if you have class A, CA, and what's the probability of observing the corresponding height to width ratio, right? And as you can see, here's a point where both curves overlap, right? So you have here a crossing point. Here is the likelihood of x given A and x given B is equal, right? At this point, you have x equal probability. As I already said, the concrete or the exact values for the parameters of this parameterized density function can be derived from a sufficient large labeled data set. So we can extract these likelihoods directly from training data. So let's go back. So what we've done on the last slides, we have done some thinking on how do we come up, how can we estimate the likelihood here, this likelihood of X given a class Cj based on training data. Because we need this to do the classification, we have to approximate this probability here. So there is a second factor, which is the prior probability of class Cj. So that's the next thing. We can improve our model of the data when we are using priors for our two classes A and B, right? Okay, so this is something we can get, for example, from a bunch of written text in, for example, in German, right? And we will see that A's are more likely than B's, right? So what we are assuming is that the priors for A are 3 times more likely than B's. So this means that the prior for class CA is given as 0.75 and the prior for class B is given to be 0.25, 3/4 and 1/4. So this is what we are working with. So, and now we can put together the base classifier for our A's and B's. So if we want to do base classification given this model, what we are doing is we are maximizing the posterior probabilities here, right, for the two classes CA and CB, and we do this by using the likelihood and the priors for the individual class, right? And we can estimate a density function for calculating the likelihood, and we can assume some prior for the class likelihood. How likely is it that the class occurs? So this was an example how base classifiers work. So the interesting thing is always how you calculate the likelihood and what priors you use. Questions so far? That was pretty dense.
Professor, I have a question.
Yeah.
Can you go to that graphical representation in which the two curves? Yeah. So, yeah, this one. So here there is a middle area in which yeah, in which both the classes overlap. So, in such cases, how we can identify whether that particular character is A or B with this theorem? Like,
so that's an interesting point that you're raising. I didn't comment on this. For example, if your random variable is here somewhere in between, yeah, So it will be classified to be an A, right? Because the probability of belonging to class A is higher than the one here, right? Based on the likelihood, all right? So you have
Okay.
misclassifications here, that's for sure. If you have overlapping probability distributions, right?
Yeah. Okay.
Do not get
So
around. But when you look at the bottom, this is not the number you're judging. You have to multiply it with a prior, right? And this even skews the situation more. So the prior reweights your decision. This is the likelihood, the decision or the probability you get from the likelihood, right? And then you're again multiplying it with the prior probability of the particular class. So you have two factors, right?
yeah. Yeah. Thank you.
What is this the answer to your question?
Yes, yes. I was
Yeah.
confused. Yeah.
So based on this, you have in this area you are basically doing wrong decisions if this is from class B, right? So you cannot classify. But this is you have an addition. This is the in addition the prior, right? Which modifies this view a bit. Yeah.
Yeah. Yeah. Thank you.
Further questions?
Professor, can you go a slide back?
Yeah.
One more, sorry. This particular part of the lecture, like, will we see the application in some later slides, or is it just for our information that you have mentioned these? Even one more slide back, you have mentioned two types of the univariate and multivariate, right?
Yes. I mean, univariate is not so interesting for machine learning, right? Because this is just one random variable, right? And you've seen already a lot that we are working with high dimensional input vectors, right?
Okay.
We deal with this multivariate normal probabilities in general.
Okay, because we have multiple inputs to
Yes.
consider. Okay.
And we have correlations between dimensions.
Okay.
Coefficients, right?
Yeah. Thank you.
And it's not always possible. I mean, these are all slightly constructed examples to visualize this stuff and to show what's going on, right? So, for example, this is optical character recognition for principle. And the feature we are using is height and width ratio. It's pretty obvious between A and B, right? So B is a large letter, right? It has a major height in handwriting and a smaller one. So we have this characteristic ratio of 1 and 2 roughly. Yeah, and this is the point that we are making here. This doesn't work when we include more letters. For example, if we would include C, right, the letter C, the probability density function of A and B will be approximately the same. So this is not a distinguishing feature. Yeah.
Okay. Yeah. Got it. Yeah.
So in real world, things are much, much more complicated. All right, but the principles remain the same, and you have to get the principle to understand why people are doing these and that things. Yeah. So this is not. I don't wanna give a lecture on Bayesian classification, but we need this a bit because the purpose why I introduced this naive Bayesian classification is the following. What we want to now show is there is a relation between the space classifier and a formal neuron with a sigmoid activation function. So let's go back to our formal neuron. Our formal neuron gets k inputs. So we have a vector x which is element of k-dimensional space. And what we assume, because we have one formal neuron, so we are considering two classes, C1 and C2. And the hypothesis now is that the Gaussian naive Bayesian classifier for two classes is equivalent to a formal neuron with sigmoid activation function. On the left-hand side, you again see the Bayesian classifier for two classes, C1 and C2. This is now more abstract. We used A and B as a quite concrete example in the previous slides, right? And now we are formulating this a bit more abstract. So we have priors for class 1, we have and 2, and we assume that the likelihoods for class C1 and class C2 are normal distributions parameterized by a mean vector and a covariance matrix. And for the proof we are doing right now, we're assuming that the covariance matrix for class 1 and class 2 are the same. Yeah. All right. So on the right-hand side, we do have our formal neuron that we introduced. So we have our inputs x1 to xk, we have the weights, we have the bias with the constant input, we have the summation, and we have the activation function. And for now, we assume that the activation function is the sigmoid function drawn here. So the function that approaches 0 when we have very negative inputs, and it approaches 1 when we have large inputs, and it's changing. So when we put this all together into a formula, so the output of this neuron is calculated as 1 in the numerator and 1 plus the exponential function with the argument minus wt times x plus the bias. Right, the sigmoid function applied to the inner product dot product weight vector and input plus the bias, and this results in this complete function. That's what we are calculating. Okay, and what we assume now is, since the sigmoid function has, we assume that if the output is larger or equal to 0.5, right? We assume the pattern X belongs to, we classify pattern X to belong to class C1, and otherwise X belongs to class C2. That's our classifier, right? We have two types, the formal neuron and the base classifier, left and right. All right. So, and now we want to prove our hypothesis that the left thing and the right thing are basically the same. How do we do that?
Professor Vorlesung?
Yeah?
I have a question to the slide before.
Yes?
You say that the bias classifier and the formal neuron with the sigmoid activation belongs together, and with the bias classifier we have the example with the two letters A and B.
Yes.
And we say we have for A a probability of 0.75, and for B we have a probability of 0.25.
Yeah.
And my question is, when I see the formula from the formal neuron, where I can see in which topic they are belongs together, I don't understand it real.
Therefore, we are doing the proof now, so you understand.
Okay.
That's okay. We have to prove this. All right.
Okay.
All right. All right. So what we are saying is, or what we are going to show is that there exists a weight vector, W, and a bias W0, such that the output of the neuron equals the posterior probability of class C1. Because what we know in a two-class problem, the probability for class C1 is 1 minus the probability of class C2. So this is the two-class problem. The probabilities are redundant, right? So if you know one, you know the other. Okay, so this is what we have to show. So, and we are starting with this posterior probability. So we have X at hand, and we want to calculate, or we want to know the probability of X belonging to C1. So we apply Bayes' rule. This is a posterior, we can apply Bayes' rule to it. And we then have the probability that we were just discussing, the probability of belonging to class C1, the class probability, times the likelihood for that class, and divided by the probability that pattern X occurs. Since we are not optimizing here, we have to stick with the denominator. We cannot leave it away. All right? But we can reformulate. The probability of observing X is the probability given by the prior of class C1 times the likelihood of X belonging to class C1 plus the probability of class C2 times the probability of class X belonging, the likelihood of X the class of the likelihood of X being class 2. Okay, so this is the first step we are taking. The next step that we can do is we can divide the numerator and the denominator by the numerator. So we will get this expression. Okay, so we have 1 in the numerator and we have 1 plus this quotient here in the denominator. And this looks a bit like, already a bit like what we see here, what the formal neuron looks like, the calculation we are doing here, right? Okay. So the next trick we are doing is we introduce the exponential function here, right? And applying a function to its inverse function is basically a non-operation. So this is equals to 1. So the exponential function of the natural logarithm of the quotient here, we are allowed to do that. That does not change anything. All right. Okay. This is the next reformulation that we are doing. We have introduced the exponential function. We have the natural logarithm of the quotient. We can exchange numerator and denominator, flip it and take it to the power of -1, right? That's again an operation that doesn't change anything. And due to the exponent rules, we can take this -1 and put it in front of the natural logarithm, right? So we end up with this expression. Right? Okay, and this looks really very similar to the formal neuron with a sigmoid activation function. 1 divided by 1 plus the exponential function of a negative argument. Right? So, and as you can see, what we have to show now is that the natural logarithm of these two probabilities here, right, is equivalent to the inner product of a weight vector transpose times X plus the bias. So it remains to be shown that the red parts are equivalent. That's a bit nasty in detail, but we can do this. So this is what remains to be shown, showing that there is equivalence between left and right side. We do some rearrangements here. Right? What we do is, so the prior probabilities, they stay the same. But what we are now doing is we are substituting this probability value by a concrete formula, by taking the multivariate normal distribution that we introduced, the formula. This looks like this, and we take the same the parameterized probability density function with the parameters for class 2 to calculate the likelihood in the denominator. Okay, so and if you apply the rules for the natural logarithm, we can separate both components. So we have one component, which is the natural logarithm, where we divide the prior of class 1 by the prior of class 2, plus the natural logarithm of the quotient of the two exponentials. When you look here at this quotient, this normalization constant is the same for both classes, right? So they disappear. So we already estimated something that looks like the bias in our formula. So we have a bias W0 prime. It's not the final bias, right? And we separate this. And we have here another part, which we assume is equal to W transpose times X plus another part of the bias. All right. So we move on with the second part, and we show that the second part can be rewritten as a weight vector transpose times X plus another contribution to the bias. Okay, so this is our quotient, and again we are applying the rules that apply to logarithmic expressions, and we can separate the quotient into a difference, and we do some rearrangements. What we have to see, what we are applying here while we are going from here to there is, for example, if you try to do this is a lot of reformulation of these different factors. It's just indicated here by the dots. We are not going to do this in detail. You have to believe me here. If you want to do it on your own, you can do it. It's not too difficult. What you have to consider is that the inverse of the covariance matrix is also symmetric. So you can assume that the inverse matrix transpose is the inverse itself. So when we are doing this, we are ending up with a factor that's calculated. It's the inverse of the covariance matrix times the difference of the mean vector of both classes transposed. And this is the weight vector. Right? The weight vector is given by this expression. So it depends on the mean values of the two classes, the mean vectors, and the covariance matrix, which is shared between the two classes. Here we have the X, and here we have a second part, W0 hat, which is given as a complex or as a difference between the mean vector and the covariance matrix of class 2 and class 1. Okay, so what we've shown is that solving the same problem, you can solve it with a Bayesian classifier using these parameters for the individual classes, but you can also use a formal neuron using this parameterization. You can estimate the weight vector from the first and second moment of the distribution and also the bias. Okay, so they are basically identical. Questions?
I have a question.
Yes?
Um,
Because do you now see how this all plays together?
this is a lot of mathematics and a little bit complicated, but can you please take the slide before?
Yeah.
Yes, this slide. And when I want to make this at home and to express this that all in numbers, when you
No, don't try to express it in numbers. It's much too complicated.
it's complicated because I think about it when I express.
First, these are vectors and matrices, right? You
Okay.
can't do it. You can't do it on a piece of paper with concrete numbers. I mean, you can do it, but it's quite devious.
It's very complicated. Yes. Okay. Thank you.
All right. This is something you have to get it. This is a proof. Okay.
Yes. Thank you.
All right. And getting it back, because you asked, you can't see where the priors come in. Priors are part of the bias. Have you seen?
Yes.
Yeah. Further questions? So this is a summary slide. What we've shown is that a formal neuron with sigmoid activation function, which is given by this formula, and this activation function, this is the sigmoid, right? Has with the parameters that are calculated from the means and the covariance matrices of the underlying data distributions, right? Actually performs a Bayes classification. So this formal neuron calculates posterior probabilities. And I think this is a nice connection between the statistical models in machine learning and the neural networks. So, all right, where do we go? Okay, I do have. Crazy. Okay, here we go. Okay, briefly summarize what we've done. We started with McCullough-Pitts and the logical function. We moved on to the perceptron. We introduced the term linear separability, and we looked at the convergence theorem for the perceptron, which is closely linked to linear separability. We moved on to other line, the mean squared error, the mean squared area error and gradients, and the idea of gradient descent, the learning algorithms. And here we had some general remarks because this mean squared error and gradient descent is one way to solve or to estimate the parameters for this linear Adeline model. There are other parameters like calculating the pseudo inverse to do that. And in the end, we have seen that there is a connection between calculating posterior probabilities as you do in statistical machine learning and what we are doing here in neural networks, because our formal neuron equipped with a sigmoid activation function calculates posterior probabilities for a two-class problem. Yeah, assuming that the inputs are normally distributed. Okay, this was chapter 3. And now we move on to chapter 4. And I want to prepare you what we are going to do in chapter 4. In chapter 4, we first look at networks, and we start with linear networks, with one-layered linear networks. So we define our linear network. We do some thinking on how we can learn in this linear one-layered network. We will see there are some problems. We get quite unstable behavior. We are stabilizing the Hebbian learning rule and derive the so-called learning rule. And for neuron, generalize this learning rule for networks, linear networks. And then we go into an analysis, because this is going to be an unsupervised learning rule. And unsupervised learning has the problem you don't define the outcome. So you have an implicit right, and we try to understand what this learning will learns from the data through analysis. And we make a connection to what's known as PCA, principal component analysis, that it has some connection with minimizing the reconstruction error. So this is what we are going to learn in chapter 4. Have you seen the slides?
No.
Sorry. All right. This was table of content of chapter 4 that I was just presenting.
Ms. Bauer, we don't see the slides.
I know. I know. I know. Now you should see the slide that I was just explaining. Okay, so we introduce the networks, we go into the learning, we analyze we extend the learning rule, we analyze the learning rule, and we connect linear networks to PCA. All right. All right. Do you see slides? Yeah.
Yes.
Yes. So let's start. Definition, what is a linear network? A linear network consists of one neuron layer, and each neuron gets k inputs, and the number of neurons in this layer is smaller or equal than k, the number of input dimensions to each neuron. And each of these neurons in this layer has a linear activation function. So this is how these linear networks are defined. And we know from chapter 2, we can rewrite this quite easily into matrix notation. So what we have, we take the weight vectors of the different neurons and make them the columns in a weight matrix. And so we are calculating the output of this network by simply transposing the weight matrix and multiply it with the inputs and calculate the output. This is pretty simple since we have a linear activation function. There is no nonlinearity involved in that. Okay. So what we have here is we have input signals which are k-dimensional vectors, and we are mapping these k-dimensional input space onto the i-dimensional output space. So our output vector y is i-dimensional, and the weight matrix, therefore it has the dimension k times I. All right. So what we further assume for our purpose here is we have training data, and we do not need labels, so we can live with unlabeled training data. So we have a set of unlabeled training data, XQ, which is, because it's input to the network, it's k-dimensional, and we have Q examples, Q data points. So these two data points do have some characteristic distribution in input space. So we can model this distribution, for example, using a probability density function or a mixture of it. So it has these data points do have a characteristic or are drawn from a characteristic distribution. So we make a sidestep because now we are introducing the so-called Hebbian learning rule. Hebbian learning rule, the name comes from a psychologist called Donald Hebb, and he had strong interest in how neurons function, and how this function contributes to what he observes in psychological processes when people are learning things. So, and what he observed working with his patients is that, and this is put into a famous sentence, when an axon A in cell A is near enough to excite cell B and repeatedly and persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells such that A's efficiency in firing B is increased. So what he's talking about is that if two neurons fire correlated, I mean they are active both, right? The synapse between these neurons should grow in strength. That's how learning works. This pretty complicated sentence is boldly put into terms in this sentence. You can say neurons that fire together wire together. That's the short form of what's written here. Hebb formulated this principle before the molecular basis of learning were studied. But what has happened, today we know that there are growth processes that are establishing Hebbian learning in the brain. So for example, let's go back again to what we've heard about biology. So Hebb's hypothesis was later on supplemented actually by molecular findings. And what biologists found was the so-called long-term potentiation, LTP, in synapses. So what's actually going to happen is, if transmitter is released, right, from the presynaptic terminal, right? So when transmitter is released from the presynaptic terminal, right, and then it docks to the receptors and excites the cell. What's going to happen if the cell is activated repetitively, the synapse, and in combination, this neuron, the purple one, fires, right? Then the synapse is strengthened. You will find more receptor molecules after a while in this synapse. So the synapses in the brain change the strengths. This is called synaptic plasticity. And today it's known to be the primary mechanism for learning and memory in the brain. So this long-term potentiation of synapses. That's how we really learn things long-term. How this is how this is implemented in the brain. So Hebb was right by observing patients, and later on, his observation was complemented by this biological finding that you have increased receptor density in postsynaptic membranes when synaptic transmission or transmitter release and firing of the postsynaptic neuron occurs.
Professor Vorlesung?
Yeah.
I have a question to the slide before where we have the two pictures of the synapse. That means the synapse strengths are changing proportional to the input and to the output?
It's changing basically according to the correlation of in and output.
Okay, and when I want to train a neuron.
Let me kick in. This is long-term potentiation. So if both are active, there is a potentiation, a strengthening, right?
Yeah.
There's also an opposite mechanism that's called long-term depression. Yeah. So it's also, I don't want to give you too much detail. Yeah. It's much more, it's more complicated. This is complicated enough what we discuss here, right? But in real, it's more complicated, but this is too much detail. This is beyond the scope. Just to give you an idea that there is an implementation for it in the brain and how it came to this learning rule.
Okay.
All right?
Yes.
Yeah. If you speak about long-term potentiation, there is also another phenomenon called long-term depression. So there's a weakening of synapses, of course. There's strengthening of synapses and there's weakening of synapses. That both occurs in parallel in the brain. And so both parts are needed to get stable learning in the brain. Yeah. But we focus on this long-term potentiation because that's basically what Hebb learning is modeling. All right. So after this long-term potentiation, this is a permanent change to the response or to the synapse. So after this long-term potentiation, the electrical excitation is usually permanently stronger for this certain connection. So this means that the postsynaptic potential for the target neuron are increased. So this is depicted here in the figure. So when you do some burst stimulation of a neuron, right, you will see that the amplitude of the postsynaptic potential after this burst, this repetitive stimulation of the synapse, will be on average higher after this burst stimulation, just simulating this long-term potentiation effect. So again here, how this is done molecularly, on a molecular basis, that's quite complicated, but biologists have studied this in great detail and there's a lot of literature about it. But this mediates this Hebbian learning principle. We can pretty easily implement it, this the synaptic plasticity described by Hebb, as a learning principle in artificial neural networks. So look at the figure below. So assume we have a neuron A, we have a neuron B, and they are connected by a weight, right? So what we do is we increase, or the change of the weight, delta W1 over time is proportional to the correlation between this output of this neuron XT, between XT and YT, right? So the input times the output of this neuron pair. So this is a background on why this Hebbian learning rule is referred to be biologically motivated. So in mathematical terms, you've seen here that we have time in here. And when we discussed how we model our the biological neuron, we said, oh, we don't care about time in our artificial neural networks. So the time aspect is probably pretty important because this correlation only is implemented in strengthening of the synapse when it's close in time, right? So in biologically that matters, but since we do not consider time in our neuron model, we skip the time aspect. So the Hebb's correlation-based learning rule says that the delta W, the weight change in a learning step, is proportional to X times Y, the input times the output of the neuron. Okay, this is the same formulation as in the prior slide, but without considering timing. So this is proportional. We can formulate this to be an effective learning step, the nth learning step of the ith neuron in our network. So what we formulate here, we formulate the weight vector of neuron I in our network. The new weight vector at iteration step n+1 is calculated to be the weight vector of neuron I in iteration step n plus a learning rate alpha times the output of the neuron I given the input xn in iteration step n times the input xn. Okay. We can make this expression a bit more explicit. We can say the output of our neurons in this linear network, they are calculated using the linear transfer function f6 applied to the inner product of the weight vector times the input, the scalar product, times the input vector. And since this is the f6 is the linear function, this is straight away. So the new weight vector is equal to the old vector plus the learning rate times the inner product of the weight vector times the input times the input. Are there questions concerning indices or anything else? This is a learning rule for a Hebbian-based learning rule for one of the neurons in our linear layer.
Professor, in this nth learning step, for example, if the machine it has learned in the fifth step only, so what will be the terminating point of this? Like we don't want to go to till nth, right?
Yeah.
So
Yeah, the termination of the learning algorithm is probably when weights do not change anymore. So you apply the learning rule and you recognize that now the weights do not change anymore. That could be that point.
okay, yeah, thank you.
We will come to this point later when we understand what this learning rule delivers.
Yeah.
At the moment, we just formulated it according to the observation of neurons that fire together, wire together, right? This is the principle implemented.
Okay.
Okay. So in mathematical terms, this learning rule has a problem. This plain learning rule, just taking this product of in and output, right? The correlation as a basis for updating weights, has the problem that it's unstable. So if you apply this learning rule, you do not have to do much thinking about how to determine when you stop learning. What's going to happen is that the weight vector will diverge, so it will grow in length. So this learning rule, so naively as it put here, is unstable. So the question is, why is it? Why is it unstable? So to understand why it's unstable, we have to do again a bit of analysis of what's written there. Okay, so again, the plain Hebbian learning rule. So the new weight vector equals the old weight vector plus the learning rate times the weight change, delta W. And delta W is calculated to be the correlation of the output and the input of the neuron. And this is again the same as we did in the slide before. Now I use the different notation. So this is V transpose times X. So you can rearrange the factors, right? And what you will get is you will get the input X times X transpose times W. Okay. So when you look at this X times X transpose, so you probably recognize that this is going to be a matrix. It's a matrix. It's weight vector. And what we do now is, because this is delta W, the expectation for the weight change is the expectation of this product X times X transposed times the weight vector. And so what we see here is the expectation of the weight vector update is equal to some matrix C, which is the expectation of this product here of the input vector times W. And this matrix C is given to be the expectation value of all the input patterns, because X is one of the patterns. And in each of the learning steps, we are choosing another pattern. So this is the expectation value of the training data times its transpose. And this is what readily described by the sum, so the average of this product over the complete training data set. So this is normalized by the number of training data we do have. And this is known to be the so-called correlation matrix. All right. So we've done some consideration on what this delta W actually is, how we calculate it, or how we can reformulate it. So delta W, we get back to time now. So we are changing our W's by this product, this matrix C, correlation matrix C times W. So in principle, we have the time discretized version system of this. These are coupled differential equations. So we can reformulate this as a first order differential, as coupled first order differential equations. So the change of the weights per time is equal to this correlation matrix C times W. And if you look at this, right, you may see that if this is the differential equation that you are going to solve, there is one solution to this differential equation, which is given to be that the weight change over time is correspondent to the exponential function with an exponent lambda t times u. So this step going from here to there, this decoupling of the differential equations, is done via diagonalizing this matrix C. So you have a matrix and you're diagonalizing it. This corresponds to singular value decomposition or eigenvalues. So let's look again. How do we come from here to there? So we have this expression, the exponential function lambda t times u. If you look at this point here, we can see when we take the derivative of this side, we will end up with a function lambda times e of lambda t times u, right? Because the derivative of the exponential function is the exponential function itself, and you have to apply the chain rule. You have to put the lambda in front of it. So on the right-hand side, we have the expression c times the exponential functions times lambda t times u, right? So when we look at this, you will easily recognize that you have a redundant factor, right? This exponential function. If you get rid of this redundant factor, you end up with an equation which is called lambda u times cu. And who recognizes this expression? What is it?
Eigenvalues.
That's an eigenvalue equation. So you're looking, this is the eigenvalue, lambda is the eigenvalue, u is the eigenvector. So lambda is a scalar and u is a vector. They are independent of time. However, they are, what we know is that for a matrix of dimension, and I think K is the, C is the correlation matrix of the data. So it's a K by K matrix. So we have several pairs of eigenvectors and eigenvalues that are solving this equation. Yeah. The correlation matrix is the same as the covariance matrix. When you look at how we are calculating this correlation matrix, right? It's symmetric. Oh. So this correlation matrix is symmetric. And it's the outer product of a vector. So for this type of matrices, we know that all the lambdas are greater or equal to 0, right? And if we have lambdas greater or equal to 0, when we look back at the original definition, at when we solve this differential equation, system of differential equation, we see that if these lambdas are greater than 0, we will see that this weight vector over time will grow and grow and grow. Yeah? Okay. Right, so this is the reason why this learning rule in its naive form is unstable. So the plain Hebbian learning rule diverges, and you can prove it. That was an introduction or something I introduced. I mean, I already bothered you in the beginning with a lot of math, right? And as you can see, there's math, a lot of math upcoming. For example, you have to have an idea about differential equations, first order differential equations. That's, again, not too complicated, but you have to have heard about it to understand it. So as you can see, there's all kind of math involved into machine learning. And this is yet another example where you need math to understand what's going on. So having this naive learning rule, you can analyze that in its plain form, it's unstable, right? Using a bit of math. So what we do next, and we won't do it today because we are at the end, and I think you've heard already a lot of different bits and bobs today. So I'm not going to continue. We are continuing next time. So we've seen the linear network. We heard about the Hebbian learning rule. We heard about that the Hebbian learning rule is biologically motivated and how we formulate it. And we've seen that in this form, as we formulated it in the first slides, it's not going to work. So the next thing we are considering is how do we transform this unstable learning rule into a stable version, right? And this is what we do next time. We progressively make this learning rule more stable, right? And see in the end how it plays out and what we are learning with a stable Hebbian learning rule. We are not learning anything with an unstable one, right? Because it just diverges. Okay, any questions?
I have one question, but it doesn't concern the topic. Next week we have online exercises, right?
No. There are yet another 2 weeks till Christmas vacation starts. So
okay.
Okay, so just, I mean, this is not so interesting for the students, but we do a lecture next week, and we also do a lecture after next week. So I probably continue till Tuesday before Christmas. So since this is a virtual thing, so we continue. And the in-person labs are in person on the upcoming Monday next week, right? But in the last week before Christmas, we do not meet in person because many of you want to visit their families, so we take the chance to isolate ourselves as far as possible, right? Before we meet families, right? That's
okay, I thought that we need to do 2 weeks isolation. That's okay. Yeah, never mind.
It's then almost, it's more than 10 days. You can probably isolate. So yeah. Okay. So in person next Monday, and then we stop in person till after Christmas. And
Okay.
we will see what happens after Christmas, because yeah, I'm not sure what's going to happen in the next couple of days concerning decisions in politics. Yeah. Okay. So we have to think week by week at the moment, right? How we do this. Other questions maybe concerning what we did today? We will have a simulation for this linear networks comparable to the one we did for the perceptron. And there we will see that the learning rule diverges under certain conditions, and you will get a feeling about what it means. Just want to remind you all the things that we are plotting on the slides and the stuff that we are visualizing beyond the formulas, right? These are all pretty simple examples because we only can visualize things using 2 inputs. And so this is just to help you understand what's behind the formulas in simple cases, and then you have to transfer it to k-dimensional spaces and more complicated situations. Yeah. So I wish you a good rest of the week. See you next week, either virtually or in person. Okay.
Thank you. Bye.
Bye-bye.
Thank you.